Hi everyone, this is Jake again. I'm a TA for Chem 285 at BYU. This video we are going to go over stereochemistry. So you've already had a little bit of an introduction in class, and if you haven't yet kind of seen everything that has to do with stereochemistry, I hope that this video is a good resource to you as you study it. So stereochemistry is a conversation about mirror images, and we'll look at an example here. So here we have carbon, and this molecule doesn't exist in your body, but we'll just throw in 4 different halogens here and a hydrogen: bromine, chlorine, fluorine, and I guess we'll also do hydrogen here. Okay, just so everyone is on the same page, this wedge indicates that it's coming out of the page or the screen at us, and the dashed means that it's going away, so into the page. And if it's not wedged or dashed, it is in the plane of the page, so it's flat with it. Okay, so let's say that we mirror this. So this dotted line indicates a mirror. And I'll put a little preface here. I don't think the mirror method is the best way to approach stereochemistry problems. It's a good way to kind of define the principle of a stereocenter, but it's a little bit challenging once we get to bigger molecules. Okay, so let's refract it over this mirror here. So we have bromine, chlorine, fluorine. Besides the fact that I drew it a lot bigger, this is an exact mirror image. Okay, and it's hard on a screen to show it, but this molecule, any way that you flip it, reorient it, it is not going to be able to superimpose over the original molecule we drew over here. Okay, it's because and Dr. Savage did this example in class where he had like these model sets, and you line up 2 of them, but the other 2 are flipped. Okay, if you're struggling with this, there's probably some other resources online to kind of show you like a 3-dimensional drawing and how they don't superimpose. But you should take my word that if you put anything over a mirror, it is kind of the identical opposite configuration. Okay, if you look at your hand, so I know I don't have a camera on me right now, but if you put your left hand palm up and your right hand palm up in front of you, you're like, oh, these hands are identical, except for the fact when you start trying to put them over each other, your palms end up being on the wrong sides, or if you flip it to get your palms on the same side, then your thumbs are on opposite sides, right? That's what we call a non-superimposable mirror image. Okay, that means if it has the potential of having a non-superimposable mirror image, that means that carbon is a stereocenter. Another term for that would be a chiral center. Okay, so if that carbon has the potential or has the characteristics of having a mirror image that is non-superimposable, I don't know why it says it's misspelled, but just bear with me. If it has the potential of having or if it does have the characteristics of having a mirror image, that means it must be a stereocenter. Okay, so let's define what a stereocenter is. And we'll look at another example and also the example I already drew here. Okay, a stereocenter is going to have or be bonded to 4 different things. Okay. And those 4 different things must be, or for example, they can be 2 carbons, but what that carbons are then bonded to even further down the chain must somewhere have a difference. Okay, and we'll look at that. A good key here is you can't have 2 hydrogens, and that's where students kind of get mixed up a bit. It must be bonded to 4 different things, and just a given fact in that is it must be sp3 hybridized, that carbon. Hybridized. Oh, that spelling is so poor. We'll just say it must be sp3, okay? That's a stereocenter. Okay, so if we look at this molecule here on the left, we see that it's a carbon, and it's bonded to a fluorine, a hydrogen, a chlorine, and a bromine. That means this must be a stereocenter. Okay, that means it must have the characteristics of having a non-superimposable mirror image. Okay, let's look at another example here. So here we have 1, 2, 3, 4, 5. That's 2 pentanol, and it has exactly 1 stereocenter, and it's that one there. We can draw in our hydrogen, and we can kind of confirm our rules. So if we look at it, it's bonded to 4 things. So just bonded to 4 things. It's sp3. And there are different groups, okay? And let me change my color here. We have a hydrogen. We have an alcohol group. We have a 1, 2, 3. That's a propyl group. And then we have a methyl group. So that's 4 different things that fits our rule. That means this this carbon here must be a stereocenter. Okay. If we look at any of the other carbons in it, we will see that, oh, this carbon here is bonded to identical hydrogens. That's not a stereocenter. Here we have hydrogens. That's not a stereocenter. Again, here, and then here as well. None of these are stereocenters because they aren't bonded to 4 different things. So they are sp3 hybridized. They are tetrahedral in shape, but they aren't bonded to 4 different groups, okay? We'll look at another example here. Okay, what I drew here is a dipeptide. We will focus on these way later in the semester, so you don't need to memorize it. You don't need to remember that it's a dipeptide. We're using it as an example because they have stereocenters in it. So I'll give you a couple seconds so you can pause the video. I want you to identify how many stereocenters are in this molecule here. Okay, so the first thing I'm going to do is I want to kind of go through the molecule, and we're looking at carbons here, okay? We're not really concerned about anything else. So if I first look at this carbon here, and this carbon is bonded to a nitrogen group, a carbonyl group, this weird carbon chain, and an implied hydrogen. Those are 4 different things. That must be a stereocenter, okay? Well, let's look at this one here. That carbon is bonded to a hydrogen, which is 1 different thing. This whole thing, which is different, But then these two pieces are the same. This is not a stereocenter. Okay. What about this one here? Or actually, no, let's look at this one. So let's look at that carbon. That carbon is, before I even jump into looking at different things, I need to look, see if it is bonded to 3 different things. And we are only bonded to 1, 2, 3, because there's a double bond. So if there's a double bond, it's impossible to have a stereocenter. So that this carbon right here will not be a stereocenter. So look at this one here. I need to turn off that feature with the erase. We have an implied hydrogen here. So we have one thing. We have a carboxylate. We have this piece over here. And we have this piece. And all 4 of those are different from each other. Okay. So that means that this must be a stereocenter. Okay. Moving forward, let's look at this carbon here. That carbon is bonded to a methyl group. This whole thing down here, an alcohol, and an implied hydrogen, all 4 being different, therefore it's a stereocenter. Okay, so that's your first task, is to identify a stereocenter. Okay. Hopefully that makes sense. Okay. Let's quickly look at a sugar molecule. And I don't have glucose and all the other sugars memorized, so I'm just doing these opposite. Okay, so this is sugar. If you look it up on Google, you'll see that sugar in the ring form looks like this, okay? So our next task is to identify how many stereocenters we have in this molecule, and I guess we should. Okay. Okay. The first thing I'm going to do is, well, I guess the best way to talk about this is to first just give you the answer. There are 5 stereocenters in this molecule. 1, 2, 3, 4, 5. You might say that, oh, if there's a wedge or a dash, it must be a stereocenter. And that's not completely true all the time. So don't let that, but let that kind of guide you to checking to see if it is a stereocenter. Okay. Let's prove that it's bonded to 4 different things. Okay. So if we look at this carbon, it's bonded to a hydrogen, an alcohol. So those 2 are different. It's bonded to this piece down here and this piece up here. I know they're connected over here, but you can see that if we start looking this direction, it is different than going this direction. So they are 4 different things. So this one is a stereocenter. The same exact explanation for all of them. Here we have an alcohol, which is 1 different thing, a hydrogen, which is our 2nd different thing. Here we have a carbon to an oxygen and an alcohol group, which is different from a carbon to a carbon, which we had over here, carbon to an oxygen, carbon to a carbon. So that must be different. I know it's getting messy, but I'm just showing you that it is different, okay? And you can do that for all of them. Why is this not a stereocenter? Well, it's bonded to 2 hydrogens. It is not, that's not 4 different things, okay? Okay, another little principle I need to teach is that we'll go back up and we'll We will redraw this one here. So when you have something dashed, or sorry, wedged like this, and there is an implied hydrogen, that means that the implied hydrogen is, so if it starts dashed or wedged like this, the implied hydrogen is going to be dashed. And you could have drawn it off of this side coming off over here, or you could have drawn it off over here. Doesn't matter. Okay. Same exact principle down here. So if we start dashed and there's an implied hydrogen, that means the implied hydrogen is going to come off wedged like that. Okay. And then dashed, wedged, dashed, wedged. Hopefully that makes sense. Okay. You don't need to draw them in. It'll help you when we start identifying the configuration. So that's when we talking about if it's S or R. Okay. Same here. Okay. Great. So I'm gonna again redraw that 2-pentanol molecule. So after we have identified that it is a stereocenter, which we proved to you we proved up here that it's a stereocenter. Your next task is to tell me if it's an S configuration or R. Okay, and we're gonna go, while we do this problem, I'm gonna walk you through the rules of it. Okay. So rule number 1 is to first identify the stereocenter. Okay. Rule number 2 is to assign priority with atomic number. So that's going to be 1, 2, 3, or 4, based on 1 being the highest atomic number and 4 being the lowest. Generally, that's hydrogen, because hydrogen has an atomic number of 1. Okay, I should have pulled up a periodic table, but if you are watching this, you know, I think I might have one in here. Let's copy it over. Okay. Okay, so we will use that to reference. Okay, so that's where we're at here. So let's look at this 2-pentanol molecule. Okay, actually, we'll talk about rule number 3 here in a second, and it has to do with giving it R versus S. Okay, so one thing I'm going to do is I'm going to draw in my implied hydrogen, and you can do it to the left or to the right. It won't change the outcome. Okay, and based on the atomic numbers, we have this carbon is bonded to an oxygen, a hydrogen, a carbon, and a carbon. Of all of those, hydrogen has the lowest number at 4, which we can see here. And then we have oxygen, which is 8. And then we also have carbon. Carbon is 6, okay? So that means that oxygen wins, getting priority number 1, and hydrogen loses, getting priority number 4. So our next task is to determine who gets 2 and who gets 3. Okay, this carbon is bonded to a carbon and another carbon, and we're like, well, they're both the same, so who wins? You need to look at what those carbons are then bonded to, and we'll do that in parentheses. Okay, so we just determined that these carbons and these carbons tied. Okay, so below it, I'm going to say that this carbon is then bonded to a hydrogen, and another carbon. So we'll do carbon, hydrogen, hydrogen. Can you see that? So this carbon is bonded to a carbon, a hydrogen, and a hydrogen, while this carbon is bonded to a hydrogen, hydrogen, and another hydrogen. We see that here, hydrogen, another one, and another one there. If we compare this to this, the carbon wins, because there's no carbon here. So that's atomic number 1, 1, and 1. And here we have 6, 1, and 1. Therefore, this gets number 2, and this gets number 3. Okay? The next thing we need to do is, from that, we're going to draw, let's get a different color, a circle from 1 to 2 to 3. Okay? That direction is counterclockwise. And if it's counter, it's going to be S. And if it's clockwise, so if it's counterclockwise, it'll be R. How do I remember that? Well, when I write my S, I start this way, which is counterclockwise. And when I write my R, like that, I go clockwise. That's how I remember. So what direction did we travel here? 1, 2, 3. That is going to be counterclockwise. So that means my configuration is S. Okay? Great. Another rule that I did not, I neglected to put in here, and it should go up here, is the lowest priority should go in back. Okay? As in, should be the one that is dashed. So the lowest priority is hydrogen, and it is in back at number 4. So that means I can follow all of these rules normally. Okay, let's do an example where it's not in back. Okay, so the first thing I'm going to do is identify my stereocenter. So my stereocenter is right here because we're bonded to a nitrogen-containing group, a methyl group, a carboxylate, and a hydrogen, all 4 being different. Okay, I am going to draw in my hydrogen that's implied. Okay. And because I know hydrogen's the lowest, I'm going to give it the priority number 4. Oh, wait. It's not going back. So I violated one of my rules. We're talking about it, the lowest one going backwards, so dashed. Okay, but there's a trick to get around this. Pretend that it's totally normal. So forget about it for a second and continue forward. Okay, so the next thing I want to do is identify the highest one that's connected to that carbon. So this carbon is connected to a carbon, another carbon, and a nitrogen. Atomic number 6, atomic number 6. Nitrogen has an atomic number of 7. So that means nitrogen wins. Okay, so that means this over here is going to get number 1. Now I need to determine if this is 2 or 3, or if this one's 2 or 3. Some people get this really quickly, and some it takes a little bit of time. Okay, so let's look at this one here. That carbon versus that carbon. Well, this carbon is bonded to an oxygen, and another oxygen. Oxygen, oxygen, oxygen. Those are all really high atomic numbers. I'm already thinking that one's going to win. While this carbon is simply bonded to a hydrogen, hydrogen, hydrogen. This one wins, getting priority 2, and this one getting priority 3. Okay, again, we're still forgetting about the fact that this one should be going back. We're still putting that on the back burner for now, okay? Let's draw our arrow. So 1 to 2 to 3, forgetting about 4. You don't draw your arrow. That, the way I drew it, is clockwise. So clockwise is R. So this configuration right here, wait, hold up. This configuration, as we have solved it, we're expecting it to be R, okay? But we are forgetting the fact that we didn't follow our rule from the beginning, okay? That means that we just flip our answer at the end. So it is not R, it's S. Okay, does that make sense? The only time we do that is if our highest priority functional group is coming out at us, okay? And it makes sense because if you could pick this molecule up in your head and spin it around and put that hydrogen going back, your arrows, the way that you drew them, would then be going this direction, which is S. Okay? So that's S versus R. Okay? So let me do a little stipulation here. If this, so if this applies, flip your answer. And I promise you it'll be right, okay? You can even redraw it in a way. You can even redraw the molecule and you will get S, okay? Okay, so that kind of finishes the conversation about identifying stereocenters, okay? So we need to first realize that it must be bonded to 4 different things and have sp3 hybridization. Then once we identify the stereocenter, we need to assign priority and follow these rules in order to give it the name S or R. Once we do that, we can start talking about isomers and their relationship with each other, okay? So let's redraw one of these molecules. And remember, this guy is not a stereocenter because it has a hydrogen, 2 hydrogens. The other molecule on the other page had a methyl group there, making it a stereocenter. So it'd be 4 different things. So just pointing that out. Okay, so let's quickly go through this and identify the stereochemistry in it, okay? Oh, my hydrogen is coming out at us. That means my rule is going to be flipped at the end. Nitrogen gets priority number 1. Hydrogen gets priority number 4. I know comparing this carbon to this carbon, this one's going to win because we have oxygen, oxygen, nitrogen, while down here we only have hydrogen, hydrogen, and hydrogen, okay? Hopefully everyone can see that. These atomic numbers are bigger than these ones. This is going to get priority number 2. This gets priority number 3. Okay, so that means my arrow goes, and let's get in the color here. 1, 2, 3. That is clockwise. So I'd originally think that clockwise is R, but because we didn't follow the hydrogen rule at the beginning of putting it in back, it must be S. So that is S. Okay, let's quickly go through the next one. So our stereocenter is this guy here. Let's draw in the hydrogen. Oh, the hydrogen's going in back. We can follow our rules as normal. We'll give hydrogen priority number 4 because it's the lowest atomic number. We'll give nitrogen priority number 1. And it's going to get a little messy. And now we need to determine if this carbon wins or this carbon wins. Remember, we're looking at everything bonded to that. So we identify the nitrogen, hydrogen, carbon, and that carbon. Okay. If we look at this carbon, it is bonded to, this carbon is bonded to an oxygen. Sorry. This carbon is bonded to an oxygen, and another oxygen. While this carbon is bonded to an oxygen, hydrogen, and hydrogen. Oxygen, hydrogen, and hydrogen. Okay. If we look at these, this is of course higher in atomic number than this group here. Okay. So then this would get priority number 2. And this gets priority number 3 over here. Okay, so we draw our little arrow. Remember, we followed our hydrogen rule at the beginning. It's going back, so we can follow the S and R rule as is. That is counterclockwise. So the way I drew it is S. Okay? That's a little messy. Your next goal is to draw the mirror image of it. And we're not going to draw a mirror because that is a little counterproductive when molecules get this big. Okay, we're going to call the mirror image, or the mirror image is where we're going to flip all of the stereocenters. Okay, and the way that you do it, all you have to do, and you need to trust me and trust Dr. Savage, all you do is flip the wedge and the dashes. And I promise you that if you go through this and assign the stereocenter, we don't have to because I'm teaching you a principle here. If you flip them, you're going to get R and R. When you do that, the isomeric relationship between these are enantiomers. Enantiomers mean all the stereocenters are flipped or opposite. Okay, so we look here, we have a stereocenter there, and they're S and S. This one is R and R. That means it's the enantiomer. Okay. Well, let's say we only flip one of them. So let's do that down here. Only flip one of them. And let's do the first one. Okay, so if we look here, this one is forgetting about the hydrogen. This is dashed, and this one's wedged. So let's just change this one to wedged and keep this one wedged, flipping only one of the stereocenters. Wedged, whoops, wedged and wedged. That makes this stereocenter R, because we flipped it, because it was S, and we didn't touch this one, so it stays S. The relationship between this one and this one is diastereomers. Should have more room. Diastereomers. What does that mean? That means some, but not one or more of the stereocenters have been flipped, but not all. Okay, so one, some, but not all stereocenters have been flipped. Okay, so if something has 5 stereocenters, you can flip one of them, 2 of them, 3 of them, 4 of them to get in a diastereomer of the original molecule. But when you flip all of them, it becomes the enantiomer when all of them are flipped. Okay. There's another type of isomer we're going to talk about called constitutional isomer and constitutional or structural isomer, and that's where the molecule is just different. But all these molecules are the same. They just have different stereochemistry. So the stereocenters are different from each other. Okay. I hope this video is helpful. It's a pretty comprehensive overview of assigning stereocenters, understanding chirality, which is just another word for that. If you have any questions, please reach out to me or one of the other TAs or Dr. Savage, and we'd be really happy to kind of walk through any of this content with you.